Trains have evolved over time. They've moved from steam to diesel to electric power. Today, trains are becoming more futuristic than ever, with maglev trains blazing a path toward the future of transport. So what exactly is a maglev train? Maglev trains are powered by sets of magnets. Magnetized coils running along the track or guideway repels large magnets on the train's undercarriage. They create a magnetic field that causes the train to hover above the guideway and keeps it stable. Power is then supplied to coils in the walls to create a system of magnetic fields that move the train along the guideway. The electric current is constantly alternating to change the polarity of the magnetized coils. This change in polarity causes the magnetic field in front of the train to pull the vehicle forward, while the magnetic field behind the train adds more forward thrust. To make this possible, maglev trains are equipped with superconducting magnets. When cooled to extreme temperatures, they're able to generate magnetic fields strong enough to suspend and propel a train car forward at very high speeds. The main advantage maglev trains have over their traditional counterparts is in their theoretical speed limit. Suspending a train above its tracks eliminates one bottleneck for its speed: friction. With this limitation removed, maglev trains are able to reach much faster peak speeds. To illustrate just how fast maglev trains can be, let's look at Japan's bullet trains. While they've long held a reputation for high speeds, their maglev variants are even faster. In a special test, the speed record of 275 miles per hour for the 300X was absolutely crushed by the L0 series peak speed of 375 miles per hour. Now let's move on to China, where the prototype of a new maglev train that could reach top speeds of 385 miles per hour was unveiled in January 2021. And yet that's not even scratching the surface of how fast we can get maglev trains to go. Even with friction out of the way, maglev trains still have one major limiting factor to their speed: drag or wind resistance. So what if we took air out of the equation altogether? This is where the vac train comes in. These are maglev trains situated inside evacuated tubes or sealed tunnels with nearly all air sucked out of them. Drag would be eliminated almost entirely in these conditions, allowing for higher maximum speeds at lower energy expenditure. Theoretically, their maximum speeds would be somewhere in the range of 2,500 miles per hour. That's about 5 times faster than the average cruising speed for a commercial airliner. As eye-popping as those figures are, vac trains likely won't sustain those speeds for the entire duration of the trip. Rapidly accelerating or decelerating to this speed would be stressful on the human body. Instead, they would spend half the trip accelerating more slowly to a maximum speed, then spend the second half of the trip slowly decelerating. Vac trains are gradually coming into reality. In 2013, Elon Musk proposed the hyperloop, a train system with a similar operational principle to the vac train. Although it's not going to offer commercial passengers the ability to break the sound barrier, it would be fast. The hyperloop is estimated to be able to reach 760 miles per hour. Testing is currently underway on another vac train project, the Virgin Hyperloop, which last year successfully carried 2 passengers along a test track spanning 1,640 feet. Virgin hopes to commercialize the concept and bring it to market by 2030. Now let's go deeper. What if these high-speed trains could run between continents? It may seem like a pipe dream, but some of the futuristic design requirements for this already exist, such as the underwater tunnel systems vac trains will inevitably need to pass through. Let's take a look at the Channel Tunnel, connecting the United Kingdom with France. Most of its length of 31 miles is underwater. The Channel Tunnel took about 6 years to build and cost almost $6 billion. Scaling this up would take a lot more time and resources. In 2014, China proposed a train line that would start in northeastern China, traverse Siberia, pass through a tunnel in the Pacific Ocean, cut across Alaska and Canada, and reach the continental United States. The project is estimated to cost over $200 billion, requiring thousands of miles of new railway infrastructure to be built, including a 64-mile section under the Bering Strait. It is speculated that this line could take anywhere from 12 to 15 years to complete, and in the meantime, we'll have to make sure our VAC trains can travel at this scale. But all of this being said, wouldn't futuristic, high-speed train systems be a magnificent sight to behold in our ever-expanding, technology-driven world?